Good afternoon, sir.
Hmm. I am trying to upload the manual for today's experiment, that is Manchester coding and decoding. It is getting delayed as there is some internet issue. So now I think it will be uploaded. You just go to the file section, okay, and check whether the manual for file for Manchester coding is there or not. Is it coming? Are you able to see it?
No, sir, it's not visible. Yes, sir, it's visible.
Yes. You just start reading the manual and then I will go to the lab and demonstrate the experiment. Start reading the manual, all of you. Manchester coding hardware. Okay. There is another experiment that will be done using software. So this experiment is hardware based. मैनचेस्टर कोडिंग आ रहा है ना इसका? the terminal से output आएगा. Okay, so are you studying the manual of Manchester coding?
Yes, sir.
What is the advantage of Manchester coding? You have studied in data communication.
Sir, it is helped in clock recovery, sir.
It is
The
helping clock
EC
recovery.
component of the encoded signal will not be dependent on the data.
Is there any DC component?
No, sir.
So if DC component is present, then there is consumption of power, unwanted consumption of power. So it is one. So it is that is one drawback, and here you see that in generally Manchester coding, what happens if you in normal coding, what happens if you transmit one logic one, so that actually has some DC value. Okay, so that DC value would be transmitted. So it will consume some power in the circuit. So that is so to avoid that, some coding techniques, line coding techniques are used. So there are many coding techniques like RZ, NRZ. Okay, so in case of uh, Manchester coding, what happens when logic 1 is there? Uh, so that logic 1 actually is converted into a bit where half of the portion of the bit will be 1 and half of the portion of the bit will be 0. So there is transition at the middle of the bit. Okay. So that is the concept of Manchester coding. So DC component is removed. So this is one advantage. So, but some other drawback is there, that is it is not bandwidth. Actually, when we talk about bandwidth, it takes slightly bandwidth, more bandwidth than the other coding techniques. Okay, so but still some has some advantages. So when logic 1 is present, so there is transitions and the middle of the bit, that is from logic 1 to 0. And when logic 0 is there, so there will be transition from 0 to 1 at the middle of the bit. Okay. So that is the way how the Manchester coded data is generated. And another important advantage is that it is a self-clocked signal. Okay, so you need not transmit the clock signal. Okay, so when it is received by the receiver automatically extract the clock, okay, from the Manchester coded data itself. That is one big advantages. So in that case, there is always require where there is no requirement of maintaining the phase and frequency of the clock. So the receiver automatically extract the clocks from the Manchester coded data. Now, how the Manchester coded data is generated? So you can see the block diagram, the experimental setup. Yeah, I will show you. So you see that we take some data, okay, we apply some data here, and let us say it is actually uh, data is nothing but a periodic signal here we consider, that is of 32 kilohertz, let us say, that is a square wave data 32 kilohertz. So 1 and 0 are alternately transmitted. So when logic 1 is there, then it consider that particular duration, that is 32 kilohertz frequency. So 1 by f is the time period. So half of the time period is the um, time durations for logic 1. Then next for logic 0. So it is not coded. This is the data you want to get, wanted to convert it into Manchester coded form. So this first this thing is shifted, half bit shifted, okay, and this half bit shifted data along with the clock. So clock is used in the transmitter. So then they are XORed. Okay? So when the XOR operation is that when logic 1 and 0, when logic 1 is their input and logic 0 is the another input, so they are 1. So according to the XOR operation, when 1 0 are present, 1 0 or 0 1, then output remains 1. So then it is transmitted through some buffer stage, and transmitted, and the optical transmitter is used, LED. Then it goes to optical fiber. Then at the output of the detector, we um, get the received data, okay, but it is in Manchester coded form. Then next step is to decode, Manchester decoding. So there is certain steps for Manchester decoding. So I will show one waveform how the Manchester coded data is generated and how it is transmitted and decoded. So, but before that, one concept is that is called bit cell. Okay. So generally, we tell that Manchester coding means at the half of the beat, the the data goes from high to low or low to high, depending on the data. But that how we decide that position, that upbeat position. Okay? That is one important thing. So that upbeat position is not always exactly the half of the beat positions. It is defined according to the bit cell or by certain duration, and that duration depends on the time period of the clock that is used. So, uh, so clock signal can be of any frequency, and one full clock cycle we consider as the beat cell. Okay? So this clock frequency is higher than the data frequency. Clock frequency is higher than the data frequency. And the data actually is divided in the form of bit cells. So suppose there is 100 millisecond bit duration, logic 1 say, 100 millisecond bit duration. So we divide it into smaller uh, durations. Let us say 10 milliseconds. So one bit cell will be comprising of 10 milliseconds, say, and that 10 millisecond is actually the frequency, a time period of the clock pulse. Okay, so total that bit duration that we considered 100 millisecond is divided into 10 bit cells. Okay? And each bit cell comprising of the bit duration of one clock pulse. Let us say we consider the time duration of clock pulse is 10 millisecond. Okay, so 10 milliseconds is the duration of bit cell. Okay, so within that 10 millisecond of bit duration, clock pulse is there. Clock pulse is also going from high to low like that. So with 10 millisecond time period. So uh, Manchester coded data is generated using the XOR of the data and the clock pulse. Okay, so you will see that I'll show the waveform here. Now I am showing you that this is your. Is my screen visible? Is my screen visible?
Yes, sir.
Okay. So you see that this is your data, logic 1, this is logic 1, and this is logic 0. Okay. So, and this is the clock pulse. This is the clock pulse. It has certain frequency, that is 1.024 megahertz. Okay. 1.024 megahertz is the clock duration, and data is 32 kilohertz. Okay. And this is the clock frequency. Okay. Clock pulses, and each clock pulse is of uh, 1 by 1.024 megahertz. That for millisecond, that frequency corresponding time period. Okay, that means 1 by 1.024 into 10 to the power 6. So that means it is near about 1 microsecond. Okay, near about, say it is 1 microsecond clock pulse duration. So this 1 microsecond clock cycle, full clock cycle duration is considered as bit cell. Okay. Now if we XOR between this one continuous long one and these smaller clock pulses, then this output is generated. Okay. So this output, you see, this is the Manchester coded data. This output is generated, and you see that, and this is generated because when 1 1 is there, that time output is 0. When 1 0 is there, that time output is 1, according to the concept of XOR gate. Okay. So whenever there is this is the bit. Okay. So we expect that at the middle of the bit, generally transition should take place, but actually it does not so. It is not so. It is actually at the middle of the bit cell, not the middle of the bit. Okay. So, and this bit cell is actually one clock pulse, clock cycle. If you assume that clock signal exactly equal to the data frequency, then it is okay, no issue. Or half of the frequency of the data, then at exactly at the middle of the bit, you will see a transition. But here, the transitions according to the Manchester coding takes place at the middle of the bit cell. So that's why there is, you see, multiple transitions for the entire duration of the bit. This is the entire duration of the bit, and you see this is the Manchester coded data, and multiple transition is there at the for the entire duration of the bit. But there is change at the transition of the data. Okay? Transition of the data. So when data changes from 1 to 0, that time you see there is gap. Okay? There is gap, or there is uh, 0 here, logic 0 for certain duration. Similarly, when data changes from 0 to 1, at that time there's logic 1 for slightly larger duration. So there is gap here. So you can see the transition of the data. Okay, the positions of the transition of the data 0 to 1 or 1 to 0, okay, in the Manchester coded data itself. Okay. So this is 1 for slightly longer duration. This is 0. So now, so this is the and this is because that this is because the XOR operation. So this XOR operation is between the clock pulse and the Manchester coded data, and some situations occur when during the transition Okay, so after the transitions from 1 to 0, okay, so data becomes 0. So that time the previous transitions was 1 to 0, and the next transition is 0 to 1. So there is slightly longer duration of the 0 bit here. Similarly, here also, previous transition was from 0 to 1, and next transition, so in the at the end of the logic 0 bit, there is transition from 0 to 1, and at the next bit, the beginning, there is logic 1. So due to that, there is transitions from 1 to 0. So that makes the logic 1 slightly longer. Okay, that makes the logic 1 duration of the logic 1 slightly longer than the other pulses. So this is the way the how the Manchester coded data is generated. Now next step is this is decode. So how it is decoded. So in the and decoded means it is not simple decoding. You have to use the clock recovery circuit. Okay. So clock recovery circuit consists of first stage is integrator. Okay. Then integrator. Then you have to use the output of the integrator. Okay. You have to XOR. You have to XOR the output of the integrator with the received data. So that is the here some concept is given that how the Manchester coded data is decoded. So you know that when clock pulse or a square wave is transmitted to the integrator circuit, we see the integrator circuit means it is low pass circuit, okay, RC low pass circuit. So there is waveform like a triangular wave, and it depends on the RC time constant. Okay. So since it is integrator, so when logic 1 is there, that time you will see the linear or straight line or exponential, slightly exponential curve. So I will show the that kind of waveform. Okay, you see that suppose your uh, Manchester your Manchester coded uh, data is square wave initially say. So when logic 1 is there, okay, so output of the integrator is this, and when logic 0 is there, the output of integrator is that is going like this. Okay. So this way, the integrator output is generated, and that integrator output is XORed. So you may note down this line that integrator output is XORed with the received data. Okay, and output of the XOR gets gives a low going pulse, low going narrow pulse for each transition of the received data. Low going narrow pulse for the each uh, the output of the XOR gate. So the integrator output and the received data is XOR. Received data is Manchester coded data. Okay, that will be XOR with the integrated versions of the same data itself. So whenever there is uh, transition, okay, of the received data, we will get narrow pulse, okay, like this. So whenever you see that this type of data, okay, so integrator output and the Manchester coded data, okay, is XORed. So at the transition of the data, transition means whenever there is 0 to 1, at that time is you will see some low going pulse, means XOR gate. Output of the XOR gate will give you low going pulse. And that low going pulse you apply to a monostable multivibrator. Okay. Monostable multivibrator. So since it will act as triggering, okay, so you select the time duration of the clock pulse such that it will match with the clock frequency or clock time period. So that way the clock signal is automatically generated. So the clock recovery circuit in the Manchester decoding stage comprises of: one is integrator, RC integrator, another is XOR gate, and another is monostable multivibrator. So three elements or three stages are required. So in the first stage, there is RC integrator. RC integrator, it does what? Um it receives the Manchester coded data in the square wave form, and it gives you a waveform like a triangular wave. Okay, then triangular wave and the received data itself it XORed. Okay, then XOR gate will produce some low going narrow pulse, okay, at the edge of each transition, and that edge of the each transition actually tells about the clock pulse. Okay. So that means clock pulse is present at those locations, and if you use that low going pulses as the triggering pulse to a monostable multivibrator, and you fix the durations of the pulse width of monostable multivibrator, like 1.1 RC you might have studied in, you can remember in pulse and digital circuit you have studied that monostable multivibrator pulse it whenever there is transitions from high to low, as which acts as triggering pulse, then it produces output changes from 0 to 1, and it will remain in that state for certain durations. Okay, and that duration is actually will be selected such that it will match with the clock signal that you have used at the transmitter. So that way you can generate the clock signal, and it will act as clock recovery circuit. That is the important thing. So once the clock recovery is completed, then you apply that recovered clock signal to a D flip-flop, okay, D flip-flop, and data you apply to the D flip-flop, Manchester coded data we apply to the D flip-flop, then you will see that D flip-flop produces your Manchester coded data. Okay, so for for whenever, what is the concept of D flip-flop? That it stores the data. It delays, means it holds the data for one clock pulse duration. Okay. So for that one clock pulse duration, it will hold the data. Okay. So that's why that way it will be used for decoding. Okay, decoding of Manchester coded data, and you'll get the data itself. So in the receiver, there are two stages. One is Manchester decoder circuit along with the clock recovery circuit. Clock recovery circuit uses RC integrator, then um, RC integrator, then XOR gate, then monostable multivariator. And decoder circuit use one flip-flop, D flip-flop, and at the D clock input of the D flip-flop, the recovered clock will be applied, and the data, Manchester coded data, will be applied to the D flip-flop. Okay, so the D flip-flop output will give you the Manchester decoded data. So that is the overall theoretical concept. Now I will show the experimental waveform. All of you are listening? Please raise your hand. Other people, what you are doing? Okay, so now I'll show you the waveform. Okay, so now right now you can see the waveform, that is data waveform. Okay, so I have taken the connection. So this is the board. Okay, that is the kit that performs the Manchester coding and decoding. You can see that there is data. We have considered 32 kilo frequency, 32 kilohertz. Okay, that is applied here to data in terminal to the clock XOR gate, and Manchester clock is generated, that is of 1.024 megahertz. Okay, using this jumper, you can use this jumper to the next point, then it will create a clock frequency of 256 kilohertz. So I have used this jumper, I have kept this jumper to 1.024 megahertz. So now this XOR gate is produces the Manchester coded data. Okay, this is the Manchester coded data. Now I will show you. So this data you can see now, and I will show the Manchester coded data. So first I will show the clock pulse. So you can see the clock pulse here, the yellow one, that is of 1.1 megahertz, almost 1 megahertz duration. Okay, and clock pulse is of 32. Clock pulse is of 1 megahertz duration, and the this thing, that data is of 32 kilohertz. Okay. So now I will show the Manchester coded data. Are you able to see the Manchester coded data?
Yes, sir.
Okay. So you see that when, let me change it. Let us consider that when the data is 1, okay, this data is 1, okay, so there is transition from high to low, multiple transition high to low, but and that actually transition is there Okay, so that actually not exactly at the half bit position. It is the up of the bit cell. Okay, so as I told that half bit cell means, and bit cell is the duration of one clock pulse. So this is the one clock pulse duration, full clock pulse, okay, from this point to this point, and transition or this point to this point. The transition is there at the middle of the bit cell, the middle of the bit cell. This is one bit cell. This is small square box. At the middle of the bit cell, there is transition, and this occurs multiple times. Now you see that for the logic 0, there is transitions from 0 to 1, 0 to 1, continuous transitions from 0 to 1, 0 to 1, like that. So at exactly at the transitions of the bit data, that is data goes from 0 to 1, you see that previous transition was from 0 to 1, okay, and this is due to the bit cell for logic 0, and for the next part, that when logic 1 appears in the data, there is next transition is from 1 to 0. So 0 to 1, 1 to 0. So 2, 1 is there. So that's why this duration of this one is slightly larger than the duration of the other pulses. So you see there is transition, and the same thing you can observe when you go for the another transition. You see for the other transition, that is transitions for high to low. This high to low is there in the data. So high to low, in that case, the previous transition was 1 to 0. 1 to 0 was the previous transition. Let me show you here. So now you see that when data changes from 1 to 0, okay, 1 to 0, that time the previous transition was 1 to 0, as it was logic 1. The logic 1 for one bit cell, not bit cell, 1 to 0. Then next transition is from 0 to 1 for logic 0. This is logic 0 data, this is logic 1 data. So 2 0 is there, 2 0 is there. That's why it makes slightly larger duration than the other clock pulse. This duration of logic 0 is slightly larger than the other pulses. So this is the waveform for Manchester coded data. And you see that another important thing, that how many transitions should be there. So you see that if we count it, okay, it is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 for logic 1 and Another 16 for logic 0. Logic 1 16, logic 0 16. So total near about 32 or 33 transitions. So this is because the ratio of the data frequency, the clock frequency and data frequency is 33. If you divide the clock frequency, that is 1 megahertz, with respect to 32 kilohertz, you will see that it is almost coming to be 33, 32, 33. So that's why 33 number of transitions are there in the waveform. So you have to draw in that way. So that you cannot draw it in shortcut form. Okay? Because I will see whether you have used means properly drawn the waveform or not. So total there will be 32 transitions one data cycle. Now if you change the clock frequency, let us say so 256 kilohertz. Now you see that it is slightly reduced. I have changed the clock frequency to 256 kilohertz. So now it will be 256. So now this thing has reduced. The number of changes, number of transition is reduced. So it is 1, 2, 3, 4. 4 plus 4, 8. So 256 divided by 33. So that means 8 number of transitions would be there for one entire data cycle. So let me keep it once again to 1 megahertz. Now I will show the received data. So I will connect this CRO probe to the Manchester received data. Now you see it is going to the optical fiber. Okay. Yes, it is a fiber optics link is there. Goes through optical fiber and receiver. This is the receiver, and then receive data. Then it goes to the this thing. Manchester coded received data. You see it is the same thing. Okay, same thing as the transmitted data. Then we see the Manchester clock, received clock. You see that this is the received clock, yellow one, and it was the same as the transmitted one. Okay. You see that both the transmitted, the upper one is transmitted clock. Transmitted means used in transmitter, not transmitted. It is transmitter clock, this one, and this is the receiver clock. Both are same. Okay. Now we will see the coded data, Manchester decoded data, and also we'll see Manchester data. We see this is the Manchester, that is the data, uh, original data that was transmitted and Manchester coded. Now this is the decoded data, Manchester decoded data. So these two are same with little bit time delay. That is due to the delay of flip-flop and other gates, other states. Both are same. Okay. So I have shown all the waveform. So now I have explained also the theory of Manchester coding. What is the transmitter circuit? What should be the transmitter circuit? What should be the receiver circuit? All these things we have discussed. Do you have doubts? Do you have any doubt? Or should I
No,
show
sir.
it? Should I show it again?
No, sir. It's clear.
Okay. Anybody else? Why all of you have not joined today? Only 33 I can see. What happened? Do you have any exam?
No, sir.
So when you are planning to come to the campus? Or you don't want to come to the campus? What is your thinking? By next week? By next week are you coming? You have to come, otherwise you will face problem during the exam. If you don't see the exam practically, the final exam will be offline, both in theory and lab. The exams will be all offline based. Practical lab experiments you have to perform in physical mode. So you have to come to the campus as soon as possible. Otherwise, you will face problem. Okay, then I am closing now.